think we're ready.
It's now my great pleasure to introduce team FORCEPS21. Take it away, team.
Okay, thank you, Nathan. And hi, everyone. Nick, Charlotte, Theo, and I are FORCEPS21. We're sponsored by Dr. Kashab's Product Development Lab, and we want to thank you all for being here. A special thank you to Dr. Akshantala for his help throughout the semester. So over the semester, we've developed new forceps to be used in biopsies of the bile duct. But before we get into what we made, let's understand more about biopsies and why they're needed. So a biopsy is the examination of tissue removed from the living body to discover the presence, cause, or extent of a disease. They're the only sure way to diagnose most cancers, and although imaging tests like CT scans and X-rays can help identify areas of concern, they can't differentiate between cancerous and non-cancerous cells. The picture to the right is actually from a procedure that we were able to observe. Okay, so for some background on the procedure itself, this video is going to detail the current SpyBite forceps and how they are used. So the white device at the top is the actuation tool that the doctor uses to control the jaws and rotation of the forceps. The black tube is the endoscope that enters the patient through their mouth, down their esophagus and stomach, and ultimately reaches the small intestine. The forceps emerge from the endoscope once it arrives at the bile duct, and using X-ray and video imaging to identify the tissue in question, the doctor then actuates the forceps and collects the sample, which you can see here.
So the design problem our project aims to address is that the current commercially available forceps aren't suitable for collecting biopsies from all parts of the bile duct. As shown here in the diagram, most forceps have a limited range of motion, so they might not be able to collect tissue samples if the biopsy site is located on the sidewall. Only 15 to 24% of all biliary structures turn out to be benign, so it's extremely important that all biopsies are not limited by position and that samples are high quality. The diagnosis failure rate is currently around 60%, and this is primarily due to insufficient tissue samples. So here we see a series of different forceps that are already on the market. This first image shows how the forceps interface with the tool of the duodenoscope, which is the specialized endoscope used in biliary and pancreatic biopsy procedures. In addition to a limited range of motion, many of these existing forceps are unable to collect tissue samples at a size and depth that is consistently useful for diagnosis. Some of these designs can chew the samples, which can destroy the tissue layers that are crucial to diagnosis, or some of them don't collect deep enough tissue samples to see the tissue layers at all.
So throughout this project, our team aims to improve forceps design to collect cleaner and deeper samples of tissue at a wider range of motion in order to yield higher biopsy success rates. In order to successfully meet this objective, the following design requirements must be met along the way. The requirements in gray are applicable to all forceps. This includes the ability to fit within the chamber of the endoscope, to be radiopaque, to stand out in X-ray view, and to be designed for mass production. And the requirements in green are specific to our forceps, and when met, will ensure better collection capabilities in existing forceps. This includes having large enough storage capabilities to collect multiple samples without extraction, be able to collect 2 to 3 millimeters of tissue sample at a rate of over 75%, and have 360 degrees of collection capabilities.
So to approach our design problem, we began by working at a 10 times scale. This allowed us to use a 3D printer for rapid prototyping, since we can't print at a high enough resolution to work directly at scale. So for size reference, the existing 3 millimeter diameter forceps are shown here, pictured next to a dime. So working at a larger scale, we're able to more fully develop our mechanisms, and we can produce reliable proofs of concept before beginning to scale down to size. This semester on the larger scale, we've explored 2 separate design branches, and we will ultimately be developing one of those into our final product in the spring. In order to test our scaled up products, we also designed a molding procedure to create a 10 times mock-up of the bile duct branch at the 10 times scale in agarose gel.
This is a depiction of our first fall prototype, the elbow design. As you can see, it has varying degree of motion for collection at different angles. On the right is a size comparison with each component called out to an exploded view. This slide shows the functionality of the elbow design as well as a test of our prototype. In the first, we actuate the jaws via wires connected to the main link and elbow components. We are able to control the jaws even when the elbow is rotated 90 degrees to either side. The second video is a test of the prototype on the 10 times scale Phantom, showing how the forceps are able to collect a tissue sample and retain it in its jaws. Next, we have our two different jaw design iterations. The shark tooth design will allow for easier incision into the phantom tissue while being easier to sharpen and simulate the eventual metal build material. It will also decrease slippage on the walls of the phantom bile duct.
So our other design that we've been working on is the suction design. You can see the different components of the design on the diagram on the left, as well as on our 10 times prototype that is pictured on the right. The design consists mainly of two concentric cylinders with an adjacent slot. And here is detailed the actuation mechanism for the design. So first, suction is applied to bring tissue into the inner chamber. Then once that tissue is in, the actuation wire is pulled, causing the cutting edge of the slot to sever off the tissue that is enclosed inside the chamber. Then finally, the actuation wire is released and the spring returns the mechanism to rest, allowing the doctor to take multiple samples without extraction. And so here's a video of us testing our prototype. So suction was applied to the inner chamber and using a general purpose water pump. As you can see, when the chamber is pulled, it collects a sample of tissue, or agar in this case. That sample is pictured on the right and measures about 20 millimeters in height, which is in accordance with our 10 times scale requirements.
So this table is intended to visualize how well we are meeting our design requirements for the elbow design and what we will focus on in the spring. For example, the elbow design received a 3-star rating on advancing through the bile duct because it is slightly too long. We plan to address this issue by reducing the length of the jaw and elbow components. The elbow design is similar to current forceps on the market in terms of manufacturing techniques, but still receives a 2-star rating due to the complexity of the working mechanisms. We hope to test the feasibility of this design through prototyping at the 2 times scale. Here's a similar table showing the requirements being met for the suction design. As an example, this design received a 3-star rating on collecting clean tissue samples, which we plan to solve by sharpening the cutting mechanism. Both prototypes received a 0-star rating for being radiopaque, which will be solved once the 2 times scale prototypes are made out of metal.
So looking to the spring, we will be implementing several design modifications to each branch before we ultimately choose which we will develop into our final product. For example, we need to ensure each design can be safely raised into position by the elevator in the duodenoscope channel, which is pictured on the right. And also in this image is a mock-up of our elbow design with shorter jaws and an elbow and the serrated tooth edges for better sampling. We're also looking to improve upon the suction design, such as ensuring the inner and outer slots are aligned when the mechanism returns to rest and fixing the vacuum seal. Both of these designs will also need to be able to rotate 360 degrees on their own axis. And finally, we hope to begin giving attention to the user interface and enact tests on real pig tissue to start analyzing our cutting forces. Our actuation mechanism is going to be based on the one used in current forceps, which is shown in the photo on the right. And pictured here is our current 10 times scale design next to what we hope to have at the end of the spring, which is a final design at scale that can be tested on a commercial training Phantom. So current commercially available forceps are manufactured using various different techniques and processes. One of these primary methods is metal injection molding, where a metal powder is mixed with a binder, injected into a mold, and subsequently the primary binding material is removed and the molded component is sintered and polished. And the second is a progressive die stamping method where sheet metal is formed by a series of stamping, drawing, and folding. These are both suitable methods for mass production, but we first need to manufacture a single example of our product in metal at scale. So for this, we plan to use emerging additive manufacturing processes, which will require less equipment and resources.
Yeah, so in efforts to jumpstart our spring vision, we have prototyped the elbow at the 2x scale using the same Formlabs 3D printer that we used to create the 10x model. So these images depict the accuracy and detail that the printer is able to produce at this size. You can see that the smaller and thinner parts were not able to be printed successfully. For example, the elbow right here cracked because it has very small holes along the surface of it, which caused the material to split when printed at such a small scale. So these results determine that our 2x prototype cannot be manufactured using our current technologies, and we'll have to outsource these methods. So one of the companies that we found that meets our 2x scale requirements is Digital Metal. Digital Metal utilizes high precision binder jetting to make complex metal parts with extremely high dimensional accuracy. The images shown on this slide is some of their work, and you can see that they can produce very high detail at very small scales. Additionally, they're able to print a combination of multiple parts without an assembly step, as shown in the whistle image, which was created in one print. This technology may prove very useful in the assembly of our elbow design. And we have been in contact with them recently, and they have confirmed that they're able to print our parts at the 2x scale with dimensional tolerances of up to 50 micrometers. They also have a process where they will go up to 3 iterations of your prototyping in order to meet customer dimensions specs. So here is a timeline of our spring semester. In order to reach the goal of a successful product at the actual scale, by the end of March, we will have selected the final design branch to be developed at the 2x scale. And April will be dedicated to client testing and evaluation at the 2x scale as well. So throughout April, we will also be working closely with manufacturers to ensure that our design will be ready for mass production.
So just to reiterate, we will spend the spring developing one of the designs at scale, and our forceps will be able to access more difficult biopsy sites and collect more reliable tissue samples, which will in turn reduce the number of necessary procedures and the risk involved with bile duct surgeries. So thank you to everyone for listening in, and we're opening the floor to questions.
Thank you very much, team. There's already a question from Ted. He asks, how do you account for different performance as you scale down the model to the 1x size?
So I can take that. Currently, we're prototyping the design at a 5x scale. We've had it printed, and now we just need to assemble it and test it. And from there, once we get the quotes back for the 2x scale from the metal printer, we'll be able to figure out what kind of mechanisms still work at the 2x scale after assembly.
Follow-on question, thank you. A follow-on question from Ted. In the suction design, how do you tag the sample for where it was collected?
That's a good question. We haven't, we plan to use food dye to mark like the tissue sample that's like in question. We haven't done that yet. And you could see it was pretty hard to tell using the clear agar. So we plan to use some color in future tests to make sure that we're collecting from where we want to be.
Yeah, that's a good approach. Thank you.
Yeah.
Thank you. Ethan Levy asks, have you considered biomems for the smaller model? I confess I have no idea what biomems is, but it sounds great.
Yeah, I'm not familiar with what that is either.
So Ethan, I hope we will need to look into that, and thank you.
Yeah, thank you.
Gordon asks us, is there a need to vary the depth of penetration for the sample? If so, how will each design help?
Yeah, so we're looking to collect 2 to 3 millimeters of tissue, the depth of which is just independent from that. I think